So the first one is rank in order of decreasing boiling points. So boiling point depends on what? Boiling point is associated with hydrogen bonding. It's like a stronger intermolecular force or whatever. So more hydrogen bonding makes for a higher boiling point. Okay. And then we also know, like from the lecture notes, that specifically alcohols are really good because they're both acceptors and donors. I believe, yeah, the oxygen part is the acceptor, and then yeah, the hydrogen attached to it lets it donate. So yeah, so judging from that, I mean, I would automatically say that this one's gonna have the highest boiling point. And then I would also say that this one's gonna have the lowest. So then let's see. And then we can also say that this one's gonna be second lowest because it doesn't, this one's only a hydrogen bond acceptor. And then does anyone know, do I have that right? I'm pretty sure it's an acceptor. The oxygen is the acceptor, if anyone can confirm.
I think you're correct.
Okay. Okay. So then we have those ones. And then for the last two, I think we have to look at the like the structure. And I'm pretty sure it goes like to see like which one would have the higher or lower boiling point. It's like this one has the most surface area, so the bonds break easier, right? So then that would mean this one has a lower boiling point. That's what I'm thinking, but I also do need someone to confirm.
It's
No,
going to be the other way, yeah. Because remember, more branching means lower boiling points for the carbon chains.
Okay.
And you also have two, or sorry, you don't have two on that one. So like the longer the chain without any branching, it's going to be a higher boiling point.
Oh wait, I'm sorry. More branching is lower boiling point or higher?
Lower. So if it's just a carbon chain, like the first one, it's got a higher boiling point. But like how the one you have number 5, there's more branching, so its boiling point is lower.
Oh, okay. Oh.
And there's no oxygen or anything, but also because it's branching too.
Okay, I can't make it make sense for myself, but that's okay. I'll just remember this specifically. So if that one has the lower boiling point, it'll be the lower number, so 3, and then that'll make this one 2. Right. Kind of good for everyone.
Sorry, can you explain that again?
Chelsea, could you explain it better than me?
So previously, and I can't remember which section it was, but we went over like boiling points and stuff of alkanes. So it was like the longer the chain, the higher the boiling point. And then when there was more branching, its boiling point would decrease because it's easier to pull apart than if it was just a one long chain.
So the longest chain will be the most, will be the lowest. The weakest.
Depends on like how the one we have labeled number 1 has 2 hydroxides on them, it's gonna have a higher boiling point because it has more H
Oh,
bond donors and acceptors. So when you're determining between the one that's labeled 2 and 3, that's kind of how you can differentiate, I guess, which would have the higher or lower boiling point.
okay. So it has a higher boiling point. So what's the difference between, because you put, if it like number 4 and number 3 and 5. Like I get 1 because it has more hydroxide. 2 is because it has a hydroxide on the side. But what's it? The hydrogen bound makes it not a higher boiling point. I don't get it. Sorry.
Hydrogen bonding does give it. So 3, the one labeled 3 has a higher boiling point than one labeled 4 because it can be both a donor and an acceptor, where the oxygen is just a acceptor. She explained it like where if it's whatever's more like water is gonna, or more soluble, it's like whatever is like water is more soluble and higher boiling point. It's kind of how she explained it in the office hour today.
So, yeah, and then that one, it talks about solubility on the next practice one, but yeah, so this ones are just OH groups. Those ones were the easiest to label first, except I guess these ones had to be kind of reasoned out. But yeah, OH, this one is an acceptor of it, like a hydrogen bond, and then this one's a donor. So it attached to like an oxygen or something. So yeah, those forces are strong. So we have like 2 of those. So that one's number 1. And then this one, yeah, is only an acceptor. So it was labeled lower. This one we automatically were able to do because it has no hydrogen bonding. Yeah, so this one was just the next like logical one because both of these ones are going to be, both 3 and 2 are going to be stronger than just the hydrogen bond acceptor. So that's how I got it as number 4.
Okay, I kind of get it.
Yeah. And then yeah, when it comes to doing between like 2 and 3, this is just helpful.
Which one's helpful, you said?
Branching, or like when there's more branching, then it means it has a lower boiling point.
Got it. Thank you.
Yeah. Okay. That's that one. So the next one is predict the major products. So the first thing you're supposed to do is look at the leaving group that you have and determine if it's a good one. This is a poor leaving group. And the only way to change it into a good one would be like HCl, so that you could donate the hydrogen to make H2O. But we don't have that, so it's not going to be able to react.
Sorry, can you explain that again? Just want to.
Yeah. So the first thing that you do in like literally any of these reactions is you look at the leaving group to determine if it's a good one. Good ones are Cl, Br, there's another halogen, and then H2O.
Iodine.
Yes, yeah. Yes, so those are all good leaving groups. And then she had an example on like the practice problems in one of these last ones, I think it was 7.2. You could, so if you had HCl or HBr, that's the only way that you could like go through with it, because then it'll do like an acid base reaction or something where this will grab here and then you'll have H2O and Cl, and then that would be able to do like a replacement or something like that.
That makes sense.
Yes. Cool. But yeah, this is NaCl, so it doesn't react.
So it's no reaction because of the poor leaving group, or just because it's the NaCl? Sorry.
It was just both because
Both.
the only way
okay.
that you could turn a poor leaving group into a good one is with HCl.
Okay, sweet, thank you.
Hypothetically, yes. Okay. So then this one is predict the product of elimination. So first, like, you go, is this a good leaving group? And it is. And then you look at the base that you have, and it is a weak base. And I usually tell that, I usually go by like, if there's an ionic bond, then you know it's a strong base. So if this was like Na OH, well, that's also obvious, but yeah, if it's a ionic bond, then you know it's a strong base. Okay. I'll just put that on the side there. Okay, so since it's a weak base, that means it'll do E1. So that means it'll do, or well, it'll become a carbocation first. So we'll draw that. Okay. So for this one, we have we could do a methyl shift, and then just right now I thought, can we do that? Because I feel like specifically she's only really said hydride shift.
Yeah,
but
you could do methyl.
Okay, cool. So
So
we'll,
both E1 and SN1 can have carbocation rearrangements. So that just means either hydride or methyl, I think.
so okay, so then we'll do a methyl shift.
So you did the methyl shift?
What was that?
No. Oh,
Yeah, so we did a methyl shift just because we can. And then, so from here, we're doing elimination, just to remember. So this one's gonna be our alpha carbon now. And then possible beta carbons are like all the surrounding ones. And the major one to form is gonna be the one that is the most substituted. So that'll be the one between these two. So that's this one. Okay, no.
It's so you gotta circle the one with the methyl on it.
Yes.
With the same shape as your should be the third one. Like you did it right. You just circled the wrong one.
Yeah, okay. Okay. What? Oh, okay, yes. Cool. So that one. Oh yeah, and that's just like zeta or whatever.
And like also a side note, I believe E1 and E2 favor, like the major products favor trans if it's possible or if necessary or whatever.
Oh yeah, that's true.
Whenever it applies, I guess.
Yes, not necessarily here because that one side is the same. Oh, that's a good idea. I wonder if she's going to do something like that. That would be messed up. Okay, that's that one. So then we could go to number 4.
Sorry, I have a question. In the lecture notes, we have some example in page 719.
Mhm.
This is, the second example. Yeah.
Uh-huh. Okay. So then,
The question
then-
is same as this one, but
is it the same? Is it exactly the same?
I
think it
couldn't,
might.
I didn't really look at it, but
Oh wait, whoops.
I don't know what.
We could go back really. I think that's
So which one are we looking at?
exactly the
saying that this
second one.
Is that one exactly the same as the one we're given? I think ours has the
I don't think
tertiary one, right?
so.
Okay, let me
Yeah,
go
no,
back.
that's not the same. We have like a, we have like a tert butyl.
Oh, okay.
So you
Yeah,
have
so
the
this part.
full, that carbon right there. You can't do a, well, if it was E2, you couldn't do a double bond with that. You have to do a methyl shift for E1.
Oh, okay. Thank you so much. Thank you.
Why did you guys decide it was an E1? Sorry.
Because it's a weak base. E1 occurs with weak bases, and then
So
I
what-
kind of explain.
Sorry, I get that. What happens if it was a strong base?
If it were a strong base, then it would go with E2. So that would just mean that it doesn't do a carbocation rearrangement because like there never is one. So you just go straight from here, like this is alpha, and then beta, which wouldn't even work, and then this one.
What, and that would answer, what answer that would be on? Would that be an
That would be that way because so hypothetically, if this were like NaOH, whatever, yeah, it would all happen in one step. So this is that
It wouldn't be a
alpha.
carbocation rearrangement, so
Yeah,
it couldn't go with the carbon we put it with originally because that's already a quaternary, whatever, tertiary carbon,
yeah,
or quaternary carbon.
yeah. So this one wouldn't be possible because there's no hydrogen there for it to like to be taken off. So it would have a double bond on this side.
Which will be the fourth one? Or no, sorry, it
let's see.
wouldn't be. It would be NR.
Well, if we did have it, I think it would be this one.
Oh, I see.
Yeah.
Okay.
Yeah.
Thank you.
Oh, or actually it would be, it would actually be this one because they prefer trans configuration because it's more stable.
Okay, sorry, I'm just trying to see the difference between them two. Thank you.
Or sorry, you don't know the difference between these two?
No, I was just asking because I wanted to know the difference between
Oh
them.
yeah. Yes. Yeah. So just strong bases, E2.
Sorry for my, I confused for the example, in the lecture notes, we have a hydride shift, right?
For this one, yeah, we do have hydride.
Okay, thank you so
Yeah.
much.
Yes, just because it's 3 degree instead of a tertiary one. It's just all we could do. Okay. That's that one. And then we could go to number 4 then if there's no other questions about it. And then there's also the other one we could practice with. So this one, you can look, my thing is like freaking out. That's a good leaving group, but this, what is this? How would you identify this like as a base?
The terpetoxide? Isn't
Yeah.
that Hoffman's rule?
Yes, because it's
So-
a bulky strong base. And we will do Hoffman. And we did say it's strong, so it'll be E2. Okay, yeah, no carbocation is formed. So, well, I guess we could just do it on here. So this would basically, well, it all happens at once. So whatever, I guess I'll leave it. So then we just go from here and you label your alpha carbon and then beta carbons. So that's one beta carbon. And then this one would be another. So let me just see. So if you were to go this way, you would have a tetra substituted. One of them, and then if you went this way, you'll just have a di-substituted one. And then since it's a bulky strong base, we go with Hoffman's, which means it prefers less substituted alkenes. So the less substituted one is this one. So this one. Does that one make sense?
Would you please show the tetra sub? Thank you.
Yes. Yeah, I'll go ahead and move it over right now. It's kind of hard. Okay. So yeah, so these are two. I should have listed this over here too. We have two possible beta carbons. So this one on this side looks like this, and then it's not tetra substituted. Sorry, because I was counting the chlorine that was on there. It's tri substituted. If that's what you.
And I think the other one is mono substituted.
Yes. Okay. Yes. But you still get the same result. But yeah, that one is mono substituted and this one's only tri substituted.
Sorry, can you explain what's the difference between tri and domo?
Yeah. So let's see. Sorry, my thing is super laggy. Okay, so when we do it between this beta carbon and the alpha carbon, which I'll label. Okay. So yeah, to count how many substitutions it has on it, you count from like this branch. So you count 1, 2, and then 3. So it's tri-substituted. And then for this one, you just count the one coming off of the carbon that the double bond is attached to. So it's just 1. So it's mono-substituted.
How did you decide that it was going to be mono tri?
You just have to count after you do the double bond, you count the amount of carbons it's attached to. So okay. This is a double bond. These are just like carbons, but we're not talking about them. Yeah, so you have one on this side, one on this side, one right here. So just like the next like break in the line, basically, like where it changes directions.
No, like why like between those two, why did you choose the bottom one, so the top one?
That's because, so yeah, we used a strong bulky base, and that's like the whole rule with that specific one, you use Hoffman's rule. So it prefers the less substituted alkene.
Oh,
Because
if
yeah,
that's the
it
case,
allows
with
for
the mono.
Yes, yeah. So then we chose the mono substituted one.
Got it. Thank you.
Mhm. Okay. Cool. So then we go to number 5. So predict the major products of the reactions. I have notes for this one in front of me. I'll just write it over here too. So for these kinds of reactions, it depends on the, what is this called?
Primary?
Yeah, I mean, it depends on how many things it's attached to, basically, yeah. So I'll just draw kind of what I have. Because I don't remember the names of the things. H.
Which number are we on? Number 5?
Yeah. And it only works. The alcohol reactions with PCC and chromate or whatever only work with 1 and 2 degree alcohols. And then for 2 degree, they both get you a ketone. So it's OH. Anyway, so those are like the rules for it. So first we look at what we have. So this one right here is 3 degrees, so nothing's gonna happen over here for the reaction. This is oxidation, yeah. This one is a 1 degree alcohol. And then we're using PCC, so we just kind of like look at our rule for 1 degree. It will make, what is this called? Let me check. PCC. Yeah, so it makes an aldehyde. Okay, so it's gonna look like this on that side. So we look for that one. It's not gonna be any of these. And it's not this one either, because it just has the hydrogen. It doesn't really have to be specified. It's right there. So that one is our product.
Oh, how do you know it's 3rd degree? Because it has 3 carbons?
Yeah, that just means there's 3 carbons attached. So yeah.
Okay.
It only has 1. Okay.
Which one is it? Oh, that one.
It's, yeah, this one. And that's very much so based on these rules right here. Okay. So that's that one. We could go to the next one then. So again, we look at this one, it's 3 degree. So nothing happens here. This one's 1 degree still. So we're using chromate. So we just look at what it creates. At 1 degree, chromate creates a carboxylic acid. So it's going to look like double bond to O and OH. So that's this one. Is that okay? Yeah, as long as you have like these rules, then you can just solve those.
Can
So
you just
then
Can you
that's
zoom into the
uh-huh.
rules? Sorry. Or I can just take a screenshot of it and then we can go on.
Yeah.
from there. Sorry.
And then I'll also put this in the notes section too. Okay,
Oh shoot.
so that's
Can you just
sorry.
zoom in?
Yeah.
Yeah, give me. Perfect. Thank you.
Okay, so then that is all of this one. So we could go on to the next one. So the Blackboard one. This one scared me for a second because I thought, I don't know, if she does that, I went to go read them just in case it said like big false. But yeah, anyway, so number 2 is a real question. So go by the E1 mechanism. So yeah, it's basically like come up with the products of E1. So let's see. Okay, so this is what we have. We can do rearrangement. I'll just go ahead and just switch it over. Hybrid shift. I guess we'll
Which
show it.
number is this, by the way? Sorry.
This is number 2 on the next one.
Number 2. Oh, okay.
Yeah, because the first one isn't really a question. Yep. Okay. So then we're gonna have the carbocation here, and then I have beta here. So it says select all possible products. So you can select this top one is gonna, here, wait, let me do it on a different one. Okay. The top one, if that one were the one that were chosen. Oh, wait. Yeah, all possible products, including minor products, I'm sure. So one of them will be D. And then if we go the other way, E is one of them. And then A is another one.
Which one could be major?
The major ones would be, let me think. Redraw it.
I think those would be A and E. I think A and E would both be major.
Yeah.
Thank you.
Oh, wait. Am I right now? So this one would be dye substitute. Because I'm thinking now only this
Oh yeah, maybe
other
that
one is
one,
major.
'cause the other
Oh,
one's
okay.
monos. Well, no, the other one, well, maybe
This
the
one's
other-
also dye
that
substitute.
one's think they're
Oh,
tetra substituted. So like the red one has 1 carbon and then the pink has 2 carbons. So that would be tetra. But the other one would be tetra substituted also, I believe.
wait.
I mean, try. I meant try. I'm so sorry. I'm so sorry, guys. Try substituted.
I'm confused now. Hold on. Okay, let me see.
I hate the get
Oh, I
my.
did this wrong. Okay, that's why I drew it wrong. Sorry.
Sorry, I think only E could be a major product
Yeah, that might
because
be.
the A, one of the,
I think the other one's also try substituted though.
could you please show
So that's
in A?
the orange one.
This is for E.
Yeah, I'm not too sure right now. I'll go ahead and check them after I draw it. And then this other one. Okay. Yeah, so then if we had this one, we'll have a double bond here, and this one will be 1, 2, 3, try substituted also. And then I'm not going to draw the whole one for the minor one, but this one up here would be just die substituted. So yeah, so both this one, so yeah, both A and E are major. Oh, I could have just looked at it on here too. Try sub.
Can you?
Sorry, for A, I couldn't find the third one. I only have 2.
Yeah,
For the third one, it's not applied because there is no any. You
It's
couldn't
attached to that
apply-
beta carbon. That's what you're looking at. You're looking at what carbons are attached to your beta carbons. That's how you know if it's mono
But there is no
di.
any hydrogen for the third one.
Yeah, but that's just for your R. That's just an R chain on. You're just counting the carbon. It doesn't matter if there's a hydrogen, whether
Oh, okay.
whether
I didn't know.
tri-substituted or
Thank you so much. Okay, thank you.
Yeah. Okay, cool. And then was someone else going to say something? Chelsea, now I'm wondering about that methyl shift that we did in the last one, because we're like, oh yeah, methyl shift is fine, but we didn't do a methyl shift with this one at all. So now I'm just wondering.
Because that one's you couldn't still couldn't put a pi bond, I don't think. Like I think
It's not
you
metal.
could, but you couldn't put the. I don't think it would.
It's not a
like,
methyl, so I don't
already-
think you could switch it out.
Oh really? Oh, okay. Is that
Yeah.
how that works?
Yeah, like I just don't think you could do it. Yeah, I didn't know how to explain that.
Just
Thank
avoid
you.
those
Okay.
arguments and just settle it
Only-
right now. Like I don't understand.
Okay, wait, sorry. Okay, yeah. So if this were a methyl, then we could, but it isn't. Okay, that's fine then. And then what did you just say you don't understand?
Oh, sorry. I'm confused. I think we're just going back and forth of this. So I was just really confused.
Okay, yeah, we could kind of explain it one
Once
more
you
time.
solve it, you can explain it to me. Sorry.
Oh, yeah, we did solve it. So so if it's E1, that means we're going to create a carbocation intermediate. So this one will be the carbocation. And then we did a methyl shift, or no, sorry, hydrogen shift. So our main thing looks, I'll just try and draw it over here. Give me 1 second. No, well. Oh wait, actually, no. Sorry.
Are we good?
Like
Or
this.
I don't.
Yeah, did you need it explained again?
Yeah, sorry. I
Okay, yeah.
didn't see what you did.
No worries. So, okay. So basically, I just destroyed our initial thing. This is BR, or whatever. And then it's gonna do, sorry, first this one's gonna come off, So we'll have a carbocation right here, and then we're gonna do a hydride shift so that we change this like positive thing over here. So this is what we'll have now, which means that this one's the alpha carbon. So then we go from there, and then you have 3 beta carbons. You have this one, and then you have this one, and then you'll have a 3rd one. And then it just says to show all the possible products. So we have one with a double bond right there, which is E. And then we have one with a double bond right here, which is A. And then we have one with the double bond up here, which is D. So those are all the possible products.
All right, why did you decide that one right there is going to be the alpha shift?
Because when you do the carbocation rearrangement, that just means it has room on that carbon for like a double bond to form. So
Okay.
so you could do it with anything adjacent to the carbocation.
And what's the difference between E1 and E2?
E2, they won't be able to do the carbocation rearrangement. So you'll just go straight from here, you'll take it off, and then this will be your alpha automatically.
And that will be the only result I can get.
Yeah, so actually that's gonna happen in the next one. So we could go to the next one then. So okay, so then if we're doing this for E2.
Oh, perfect. Sorry.
Yeah. Okay. Okay. So for this one, we're automatically gonna label this one is our alpha when it comes up. We'll have one here, and then our betas or possible betas are just gonna be the adjacent carbons. So this one, and then we also have no. Okay. So we have both of those, and then so is there something wrong with one of the beta carbons? Because in elimination, you lose a hydrogen and well, your leaving group. So we lost the leaving group on this one. For this one, there's no hydrogen attached. So that one isn't a possible double bond spot, I guess.
Would one of the answers be E?
No. That one goes over one too many. So the one that forms, we only have one that's gonna end up forming, and it's between these two. Wait, did I just lie to you? Let me see. No, I think I did. Sorry.
How will it be on the other
No,
end?
I didn't. I'm sorry. It'll be A. Yeah.
Oh, when you say it's on the other end.
Yeah.
Wait, so E2 doesn't have carbocation rearrangement?
No. Yeah, that's the difference. Because E2 is
Okay.
only like one step. There's no carbocation.
Yeah, okay.
formed. Yeah.
Okay, so
So that one is 3.
Oh, so
Um,
E was the opposite there. Or I don't know. Sorry.
E, yeah, a little bit.
E, you went over too many carbons.
Yeah,
That carbon, that double bond is showing on E is not really attached to. It's
The
the bond has to be attached to the carbon
alpha.
at the
Yeah.
alpha carbon. Yeah, sorry.
Oh, I see where I made the mistake. Okay, sorry. I went on the side. Thank you.
okay. So there's that one. We could go to number 4. Okay, so this one is rank them in order of solubility with water. So then this one we know OH, or well, let's see, hydrogen bonding means it's more soluble in water because it'll like react with the water. Right. Yeah, because H2O has a lot of hydrogen bonding, just a lot of possible ways for it to interact. So yeah, the structures that have more hydrogen bonding will be more soluble. So then we could do the most soluble. We also know that OH has a bunch of hydrogen bonding because it's both an acceptor and donor.
I think you can also use, like, this is where maybe the professor said, where it's like water, it's more soluble.
Yeah,
So the closest it relates to raw water or looks
That's
like
true.
water.
yeah, and like dissolves like. Yeah. So then this one is going to be the most soluble in water. And this one we could put as the least soluble in water. And then this one has 2 acceptors. So this one will be more soluble than this one, which only has 1 hydrogen bond acceptor. Does that make sense?
The one acceptor is because the the oxygen.
Yeah, yes, oxygen is a hydrogen bond acceptor. I'll write it on the side like the kind of definitions. Oh god, what are they all? NF, I think also. And there's another one. Is it CL? Okay, at least those.
I think
And then hydrogen bond donors are the actual hydrogen bonded to ONF. There is another one. Yeah, I guess I could go ahead and check it. No. Okay. This one. Oh, okay. I like. Never mind. Okay. So yeah, just those. Okay. No. Okay. Anyway, so yeah, the hydrogens are donors and the actual elements are acceptors. Okay. Oh my god. Okay, never mind. Anyway, so that's that one. And then here for the next one. You guys can look at it for a little bit, and then I will be back in a little bit. Uh-oh, wait. I'll stream it again after. Okay. Okay, so then for this one, did anyone like get the whole IUPAC name, or can anyone like start it a little bit? Okay, so let's start with cyclohexene.
Isn't it pent?
Net pet, yeah.
Oh, frick. Yes, I think I'm in. Oh my god. Yeah. Okay. Yeah, so I guess we'll just stop there for a second. And then you could identify right in front of that, your double bond is on 2. And then for that ending, you have to put in where the OH is before the suffix. Or, yeah. So 2 cyclopentene 1 all. And then there's also the methyl attached to it here. Okay, and that's just 4 methyl. So yeah, that's how you name those ones. Is that one good with everyone?
Yeah, it's good.
Okay, this one predict the products. So let's see. First, you just like label what they're attached to, 1 degree, and then this one, or secondary. So that means, and then this is with chromic acid. So I'm looking at my notes. Chromic acid for a 1 or primary is going to get you something with that's a carboxylic acid, I'm pretty sure, right? I think that's what it's called. Yes, it is.
Yes.
Yeah.
So there's that on that side. And then for secondary, either PCC or chromic, whatever the heck gives you a ketone. So that one is C. And then you for sure should just have like those notes I had on the last one. Just tell you what everything gives you. There's that. And then for this one, we'll do PCC. Secondary. No, that was primary. So that's gonna be the same for either PCC or the other one. So ketone on this side, primary gives you, with PCC, it gives you an aldehyde. So one that looks like that is A. Cool. Oh dang, that's the end of it. Do you guys want to go over anything again? It's oxidation.
Can you go
I
over
think
number
it's-
6 again? Sorry.
Yeah. So yeah, that's the same thing with the oxidation rules that I think you took a screenshot of.
Yeah.
Stop it, Savannah. Okay. No. Okay.
Nice.
Yeah.
Oh, so I see what you're doing. And then you have the O because it's a 1 degree.
Yeah.
So it depends where that 1 degree is on there. So it doesn't depend on the 2 degree at all.
What do you mean? Well, 2 degree, it gives you, yeah, okay. The 2 degree gives you the same product for both of them, for both PCC and what is this called? Chromic acid. But those are, yeah, just based off the rules that I had in the other one, just this one. Yeah. So those are the rules that I'm looking at when I do them.
Okay. I'm pretty sure it's this one.
Yeah.
Oh yeah, I have it.
Yeah, you can.
Thank you.
Yes, so that's the easy way for the oxidation ones. Any other kind of like questions or things to review? Eliminations were a bit of a struggle, kind of. I guess the main things for elimination is just E1 is a weak base, and then E2 is strong base. Those like the most important characteristics of it. Okay. So yeah, that's it for these ones. If you want to go over any again, we could do that also. I could stop recording.